Hello, everybody. I'm Kyle Hart. I'm here to talk about TESS. So yeah, let's just get right into it. All right, so TESS was created as a logical follow-on to the Kepler Space Telescope. It was proposed in 2008, began operations in 2018, with the specific goal of finding and characterizing exoplanets. While Kepler did have a lot of really amazing contributions in exoplanet science, TESS is much more focused on finding candidates that are very suitable for follow-up spectroscopy and observation, specifically with the subsequent launch of JWST. So as you can see on the graphic right there, these are the TESS viewing sectors. I have a little bit more detail coming, but as you'll notice, the red right there is the highest cadence of like the most viewed sectors on the ecliptic poles by TESS, and they completely coincide with the JWST continuous viewing sector. And there's already been some good science done by JWST as follow-ons to TESS. So the mission itself had the objective of searching for super Earths, i.e. rocky planets between Earth and Neptune size with a fairly broad range of orbital periods, anywhere from a few minutes to a number of days. While this is still too short for habitable planets on a sun-like star, if you think about M-class planets like red dwarfs or red giants, is these orbital periods actually could find rocky planets in the habitable zone. So the design of the instrument was completely centered around these mission goals. Specifically in regards to bright stars, they chose to use a CCD with an extremely high dynamic range and a very, very fast readout time. So I believe this CCD has a well depth of 200,000 and it reads out like once every 2 seconds. Same thing with the aperture size, especially designed with the detection of exoplanets in mind, and a bandpass centered around the eye, but also goes pretty much up to the red limit of silicon CCDs. The sampling, in keeping with the periodicity goals, is there are 2-minute samples that allow for really good astroseismology and characterization of these transiting exoplanets. Okay, so I'm not going to read through all of this, except for, I should say, 4 mosaics chips. But so the satellite itself has 4 cameras, and each of these cameras has 4 mosaic chips with an extremely large field of view. Each camera has a 24 by 24 degree field of view. So that's a total of 24 by 96 degrees of view on the sky. I'll have a little bit of illustration of that later. And of course, you'll also notice the extremely large pixels. However, those still do work for the science that we're trying to get with. Skip that one, go back to it. So as the data products that come off of this instrument, there are 2 main ones. So the chips themselves is, while they have these 2-second streaming readouts. And of course there's no storage capacity to keep every single one of these 2-second readouts. So what we do is stack them for 2 different data products. The first one is we'll stack 60 of them to create a 2-minute full-framed image. And then we cut out these sub-pixel arrays on special targets of interest. These are candidates for exoplanets. And then save these sub-pixel array stacks, ship them down whenever the spacecraft reaches the deep space network in its orbit. However, what I'm more interested in, and I think the multi-messenger community might be more interested in, would be the full-frame images which are generated by TESS. So as much like the postage stamp, as we stack hundreds of these 2-second readouts, sum them together to create these full-frame images. For the prime mission, it was 30 minutes. In the subsequent missions, it created a lot shorter stacks, therefore a lot higher of a cadence. And then whenever we get the downlink with the instrument, these full frame images are submitted to one of 2 different calibration pipelines through MIT and NASA. That'd be the Spock pipeline and the TICA pipeline. So going back to the mission itself, so you kind of see right there, that is a single TESS pointing. In the northern and southern hemisphere, there are 13 pointings on each of them. We call these TESS sectors. So TESS will stay on a single sector, make continuous observations for 27.4 days. It'll go through 13 of these sectors, creating a single cycle, which is about a year, then it'll flip and observe around the other ecliptic pole. The main difference between the prime mission, extended, and second extended missions is the only thing that was really adjusted in terms of science was the cadence of those full frame images. So as data that's coming off the prime mission, the cadence is a little bit slower. We have 30 minutes between full frame images. However, with the extended mission, we get down to the first extended mission has 10-minute cadence for full frame images. And then the one that we're currently in is 200 seconds, which is, I'm kind of tired right now. So we're currently finishing the second year of the 3-year second extended mission. That's going to be finishing in about a week or so on October 1st. And then spacecraft is going to flip and continue its final cycle of the second extended mission. Currently, the third extended mission is still in proposal phase. So next is I have a number of illustrations to kind of show you the capabilities of the TESS satellite. So these are a number of different transient events. They're peak absolute magnitudes with characteristic timescales. So it is, like I said, is with Exoplanet, TESS is concentrated on near and bright. Is same thing with transient events, science that we could perform anything within the distance of Andromeda. We could basically cover all of these different transients. Virgo, we lose a little bit, and then the Coma cluster lose a little bit more. The cutoff of this red region right there coincides with the length that TESS will sit on a specific viewing sector. However, like I said, near the ecliptic poles, there are some targets that will just get viewed sector after sector after sector, so there will be continuous coverage for them. I have an example of this later. Coverage area. So this is a number, this is 2-scale. This is a number of wide field of view survey satellite or survey telescopes. LSST, Pan-STARRS, should be a second Pan-STARRS, like right there. ZTF, which has a really large field of view. Start comparing these to others. So Atlas, that's the number of pixels that Atlas has up on the sky right now. Assassin has a little bit smaller cameras than Atlas, but that's how many pixels Assassin has on the sky. That's how much sky TESS is viewing compared to all of these other surveys. So we talk about sending out these GCNs and all these different notices where you want to like get these fast slew telescopes to go point. TESS is really cool is because you could just, a lot of stuff just happens in field of view, which I'll show you. So science that has been found within the TESS data, I'm not going to go over all of these because I don't have time or the requisite knowledge to do so, but we have found over 1,400 supernova in the first 80 sectors. In my references, I have citations for pretty much all of these, but I do want to talk about two in specific, two transient events that have been found in the TESS data through multi-messenger. So first is GRB 230307A. So this was a gamma ray burst that resulted from either a merger of two neutron stars or a neutron star and a black hole. I'm not sure if it's been confirmed yet, but as you can see, is I have the timeline of the detection of this from Fermi to the follow-up observations by Gemini South, which managed to capture the optical afterglow. However, the one thing with gamma ray bursts is in addition to the optical afterglow, there's also a prompt optical emission that very rarely ever seen. I think it's just a couple dozen that have ever been detected. Well, the TESS, because it was already sitting on this, is managed to get that prompt optical emission in the data. And it is pretty clear because we do have that very high cadence. And it just so happened, it was only a matter of days after this event happened on March 7th that we got that downlink. We get the downlink, like I said, twice per sector, so that's once every 13 days. So approximately 4 days after the event, we already had the test data going through the pipelines. I don't know exactly what day they ran the pipeline on this. I asked my colleague Michael Fajnan, he didn't answer my email in time, so it's just there. But they already had a paper out on the TESS observation of this within a week. So it's a really good example. Second is a tidal disruption event. This is Assassin 19BT. So like I said, so this specific tidal disruption event, TDE, lied within the TESS viewing zone. So these dots right there, that's really a downsampling temporal wise. There's hundreds and hundreds and hundreds of observations of this light curve in the TESS data. The chip gap between sectors 5 and 7, as I said, those 4 mosaic chips per camera, there's a 2 millimeter gap on there. And it just so happened for sector 6 that this specific target was in that 2 millimeter gap. And then there's a subsequent gap in sector 8, which was an instrument malfunction on the spacecraft. So nobody got any data on anything. Well, not for TESS. But there was an extremely good characterization of this TDE and a lot of, so after it was found by Assassin, multi-messenger, so within just a couple of days, we had spectroscopic follow-ups by Magellan, then Swift UVOT. I missed the talk this afternoon, so UVOT, XIRT.
Either's good.
Huh?
Either is good.
UVOT or UVOT?
UVOT. I say UVOT, other people say UVOT.
I say UVOT. Thank you.
I say
So yeah, and then yeah, so and then also this, yeah. So that's the two things that I really wanted to illustrate about TESS before I go into kind of my own plug here, is the extremely high cadence and the extremely high field of view. Is for these transient events with a high field of view, with a very large field of view, there's a really good likelihood that your supernova or your cataclysmic variable or whatever might just lay in the field anyway. Guess what? If it does, you're going to have every 10 minutes, you're going to have a really well-defined photometric data counterpart for it, which brings me to what I want to talk about. So last year I was here talking about the Assassin sky patrol system that I built. This year I'm here talking about the promise to finish building the TESS patrol system, which is a forced photometry service that we're building on this TESS data. So as we have all these sectors of data, currently we're funded to provide forced photometry for the prime mission, extended mission, as well as the second extended mission. However, we're still trying to find funding to provide the photometry and get the storage space to get all those full frame images for the subsequent extended missions that are coming up. So this is the interface from this. If any of you guys have used the Atlas Sky Patrol system, it's basically identical. We use the same web developer, he's good. Except for we have an account-based system. Because we basically threw a lot of compute at this, a lot of cores. So we're able to give you these forced photometry light curves extremely quickly. You're not going to be putting in an email request and like waiting for like hours. It should come back within minutes or seconds, depending on how long the curve you want. And then last year, per review and talking with everybody, as opposed to just looking up by raw coordinates, as you can also do Sinbad lookups and get your targets and the light curves from there. In addition to this web portal, I'm also creating a Python client to be able to query this. So as long as you go onto the web, create your account, you'll be provided with a token that you could put into the Python client, get light curves in PANDAS format, same as if any of you have used the Kepler light curve utility or the Assassin sky patrol utility, exact same format. You can push them all together and do a lot of cool stuff. When it's finished, I'll definitely be plugging it into Astro-COLIBRI, and should be finished in about a month or two. Really hope that I'd have it by now so I could provide you sample, but computers are hard. So anyway, I'm not sure how much time I have left, but that's all I have to say. So any questions?